Hello and welcome everybody. Hello Nathan. Good
Hello.
morning to you. Hi. I think I can't hear you, so maybe we need to indeed switch your sound. Maybe it's me. Let me see. Maybe you say something again.
Yeah, can you hear me now?
Ah, yeah. Now I can hear you fine. All right.
Great. Okay,
Perfect.
good.
Good. Maybe I need to. All right, here we go. So this should be good. Let us know in chat if you have any audio issues, but I think that sounds good. My audio was just too low. Yeah, welcome everybody. Good morning, good evening, good afternoon, wherever you're watching this. Let us know in chat where you're watching from, and maybe give us a quick overview of what the audience is looking like today. Thank you, Nathan, for joining today. Yeah, thank you for taking the time. So I'm looking forward to this. You are not the first time on this stream, so maybe people recognize you. It's a new face a little bit, but also an old face with not being ageist. This is truly meant of you being here before. So yeah, how are you doing?
Oh, I'm doing very well. It's great to be back, and I think we've got a fun topic to talk about today.
Yeah, I think so too. It's gonna be cool. I saw your blog post. When was it? A couple of weeks ago, and I really thought, okay, this is cool. I hope we can get this going on the stream, and I'm really happy that you said yes immediately. Let's do it. So I'm really excited. Uh, but yeah, maybe you wanna share a little bit what's been new with you over the last couple of months. Last time since you appeared here, I guess, was for maybe Notes 2021, I think. Yeah.
Yeah, well, the biggest change for me professionally is that I have joined the Neo4j professional services team as a data scientist, and it's been really wonderful to
Yeah.
be on the other side of that relationship. I've worked with the professional services group as a customer, and it's been really fun to be able to get involved with some very interesting projects using the Graph Data Science Library, and being part of this team at Neo4j has been really, really exciting.
Cool. That's good to hear. So welcome again to the team. Welcome to Neo4j, Nathan. So yeah, I mean your session, the title of your session at least is create a similarity graph from node properties with Neo4j. So I guess that's what we're gonna do today. Graph data science being a very interesting topic and a very vibrant one with lots of things going on, lots of excitement from the wider community across um, all the globe basically. So how did you come up with this topic? Was this some kind of outside push towards this, or how did you think, oh, this is a cool idea to do?
Yeah, well, Neo4j Graph Data Science Library has included these similarity algorithms for a while,
Hmm.
and so I was looking for opportunities to practice with them. And then also, I've run into situations where people think, I know I'm curious about a graph database, but I don't necessarily know if there are a lot of relationships in my data. And I think many times the relationships are there, but they're just not apparent at first glance.
Hmm.
And so I was interested in showing an example of how we can use data science to uncover those relationships and then really get a visual and interactive experience of the structure of the data using Neo4j tools.
Okay, no, that sounds good. Yeah, I think similarity and a couple of these, these high, almost like poster picture algorithms, like similarity, community detection, page rank, and stuff like that. I think they always come up, and yeah, I always read them a lot, and then it's really good to see some you read about them, or at least maybe it's just me, but I read about them and I think, okay, that's cool, but how and why, and then I get lost a little bit, but then I see a application on and like a use case or a little demo like the one we're gonna see in over the session today is really making it click for me, and it's like, okay, now I understand. This is exciting. Yeah.
I hope that this example, I mean, I think this is an example that can apply in almost any context. If you have just a group of items that have certain properties associated with them, there's always relationships hidden within that data. And so it could apply almost any context. Any list of data that you have could take this same pattern and apply it.
Yeah. Yeah, that's also a nice thing about graphs. In the end, is once you understand that they are really this multi-adaptable, very universal concept, you can find a way of making them work for you in almost any scenario, really. So yeah, that's really good. Cool. I think we can. Shall we dive in?
Let's do.
Yeah. And we want to make this as it is a live session, right? We want to make this interactive, and we can make this interactive. So if you have any questions, if anything comes up during the demo and the presentation from Nathan, then please type it in chat, and we will try to either directly answer them or at least find some time in a break where we can dive into these. So post actively, please.
Absolutely.
Yeah.
Shall I go ahead and share my screen?
I guess that, yeah, I think that would make sense most of.
All right, are you seeing my Neo4j sandbox?
Yes, your screen, cool. And let me
get
that out of the way. All right, cool.
So this demonstration that we're going to walk through, I'm going to be using Neo4j Sandbox. So if you want to try to code along at home, you could, or come back and watch the video later. I just signed in to sandbox.neo4j.com, and so you don't have to have any credit card, or it's completely free. And you can get started with Neo4j very, very easily here. I'm using the sandbox because it has the graph data science library already loaded. So there's no install or anything that we have to do to be ready to walk through this exercise. So I'm going to choose a blank sandbox because we're going to load our own data. And then I click on create, and it's going to set up a Neo4j instance for me. We can see that it's launching here. And now that it's ready, I can click open, and it will get started. I'm going to come back to this other tab because it has the connection information. I click on connection details there, and then I can copy this password. The username is Neo4j. So now that this is fired up, I will enter those credentials.
Maybe quickly, while this is loading information, this is not going to work on Aura Free because if you are already using Aura Free and you're thinking maybe I can use that, it's not going to work because this is using the graph data science library, which is not part of Aura Free. So you need to do this in desktop or sandbox.
That's exactly right. Yeah. Okay, so here I'm going to sign in and connect. Great. And now that I'm signed in, we've created a browser guide for this demonstration. And so I can type :play and then census-similarity. And that brings up this browser guide, which is just kind of a tutorial format that will allow me to copy and paste the code very easily, and it has some explanations that go with it. So I click this pin here, and that's going to keep the browser guide at the top of my Neo4j browser session. And here this describes how we're going to be exploring the concept of similarity, which is a fundamental concept to data science for any kind of a clustering algorithm that we run, whether it's traditional clustering algorithms like k-means or hierarchical clustering algorithms. We're always trying to find examples in our data set that are like each other, and then we want to put those into the same group. And so that's really the basis of what we're doing today. And the data here comes from the United States Census Bureau, and it's information about metropolitan statistical areas, which are the large cities and their suburbs around the United States. And the data comes from the 2019 American Community Survey 5-year estimates provided by the Census Bureau. So for each metropolitan statistical area, we're going to look at the population, the median household income, the median home price, and the percentage of the population over age 25 with a bachelor's degree, so a measure of educational attainment. And if you want to do this later on your own, you can follow this hyperlink and go out and download different properties. I just chose those 4 because I thought they would be interesting, but there's many other pieces of demographic data about these MSAs that you could choose to use to create this similarity graph. So the very first thing that we're going to do before we load the data is to create a constraint in the graph. And this is the code that we use here. And to run this code, I can just click on it, and then it copies it up here into the top bar. And then this triangle will run the code, and it moves it down below my pinned thing. And there we go, it executed. So what this is doing is creating a constraint on the nodes with the label MSA, and it's going to require that those nodes have a unique value for the node name. And that is going to make our data load go faster. It's also going to help us when we look at this data in Neo4j Bloom, that we'll be able to search for nodes by that name, and Bloom will be able to find them for us. And I can tell that it did something because now when I come over here and click on this database icon, it knows that it's expecting to see nodes with a label of MSA because I created that constraint. So I can tell that it worked. So I can come over here and click on this arrow to advance to the next slide. And now we're going to load the data from a CSV file that's on GitHub. So if we look at this code a little bit, I'm actually going to copy the location of this file so we can see what the file looks like. Open that in a new tab. So this file has the name of the MSA, the population, the median home price, the percent over 25 with the bachelor's degree, and the median household income. And it's just formatted as a comma-separated value file. So this query is going to read that file in and read every row. And I'm going to filter it to only the rows that contain the word metro in the name. In the file, I think I have some micropolitan statistical areas. These are the very small cities or more rural areas. And then we have the metro areas, which are the bigger ones. And we're going to look at just the metro areas for this exercise, but you could go back later and include the micropolitan areas or just do the micropolitan areas by themselves if you were interested in the rural areas of the United States. And then we're going to create these nodes, and then I'm going to set the properties on the nodes. And when I use Loadcsv, it automatically thinks that everything is a string. So I use these 2 integer and 2 float functions to convert those properties into integers and floats. So we'll run this. You can see it's running here. And I can see that it loaded lots of MSA nodes. And when I hover over one or click on it, I can see that it also has these properties: median home price, household income, percent with a bachelor's degree, and population, and also the name of the MSA came through. So it looks like our load was successful. Now, when we talk about how similar these cities are, we're going to use something called the Euclidean distance, which the Euclidean distance formula is just an extension of the Pythagorean theorem, which says that when you have a right triangle, that the square of the length of the hypotenuse is equal to the sum of the square of the other 2 sides. So many years ago, I used to teach geometry to high school students, and they would ask me, when am I ever going to use these theorems that you're making us learn and prove? And well, today is the day that we get to use the Pythagorean theorem. We're going to extend it a little bit to 4 dimensions instead of just 2 dimensions, because we have 4 properties that we're interested in. But it's really just the same idea. It's the sum of these squares, square differences. Then we take the square root in 4 dimensions instead of 2 dimensions, and that's going to give us the Euclidean distance. So this is the way that we're going to tell how far apart any 2 metropolitan statistical areas are in 4-dimensional space. So before we calculate those distances, it would be good to get some kind of a picture of the distribution of the different properties that are involved. So this query is going to match all the nodes, and then it's going to look at those 4 different metrics and find the minimum, the 25th percentile, the median, the 75th percentile, and the maximum value. So just to give us a quick picture of what the distribution of these metrics might look like. And when I look at the results here, I can see that these statistics are actually very different. The population statistic runs from 54,000 all the way up to 19 million. So that has a huge range compared to the percent with a bachelor's, which runs from 12 up to 62. So if we would just calculate the distance on these raw numbers, the population is going to dominate the calculation, because the differences in population are so big compared to the differences in the percent with bachelors is almost negligible compared to the other statistics that we're looking at. So we're going to have to do something to reshape this data to make each of these 4 statistics have a more equal weight, if that's what we want to do. The other thing I'm noticing as I look at these percentiles is that for population, the difference between the 25th and the 50th percentile is about, well, it's less than 1 million, right? And then when I look at the difference between the 50th percentile and the 75th percentile, well, it's not even less than 1 million, it's less than 100,000. There's no commas in there to help me, but yeah, it's only a difference of less than 100,000. And then when I come to the 75th percentile, it's about 300,000. So this is not evenly distributed across the space. It's not a bell-shaped curve or a normal distribution. So that also tells me that it might benefit us to try to reshape this data into a different distribution before we do the distance calculation. And in fact, here I've downloaded this CSV file into Python and created some histograms so that we could look at the distribution of the data. And so you can see on population that most of the cities are clustered here in this smaller range, and then a very few of the cities are at the very extreme upper end. And so if we would just use the raw data to do the distance calculation, population isn't going to be a big factor in separating most cities from each other. Most of them are clumped here, and then there's a very few out here on the end. However, if I apply a log transformation to the data, then it spreads this clump out more, and so that I can see the differences that were kind of obscured here. I can see them much better on this log scale. And that sort of makes sense to me intuitively, because if I would think of the population of New York City and add 10,000 people to it, it might not make that much of a noticeable difference. But the population of a much smaller city like Columbia, Missouri, which is a small town not too far from where I live, if I added 10,000 people there, it would be a big noticeable difference in the population of that city. However, if I added 10% to the population of New York or 10% to the population of Columbia, in both cases, that would be a noticeable difference. And so by applying this log transformation, we're looking more at what a percentage change would mean rather than an absolute change in the number of people who live there. And the same thing is true if I look at these other histograms for median household income. They're not as extreme as population was, But for home price and for household income and percent with bachelors, really all of them look a little bit more like a bell-shaped normal curve if I apply that log transformation. So I'm just going to apply that log transformation across the board. So on the next slide here, when we look at that, I am going to match each MSA, and then I'm going to create new properties for the log population, log median household income, log median home price, log percent over 25 with the bachelors. And the thing that is cool to notice here is that I don't have to do some kind of a tricky alter table thing to add these new properties onto a node in my graph. I could just figure out, you know what, my model needs to change, and I can evolve the model by just creating the new properties on the fly like that. So we'll execute that. Great. Now the next thing that we want to do is apply this min-max scaler. And this is going to take all the data and rescale it so that the smallest value in the data set is going to be 0, and the largest value in the data set is going to be 1. And then all the other values are going to fall proportionally in between 0 and 1. And this is the formula that we have. We're going to take each value, subtract it from the minimum value for that statistic, and then divide the whole thing by the range, the difference between the maximum and the minimum value for that statistic. So to do that in Neo4j, we're going to use the graph data science library. And when we work with the graph data science library, usually we're wanting to look at the entire graph at once. With regular Cypher queries, usually we anchor someplace and then we expand out, traversing the graph one hop at a time. But with graph data science, we're interested in things that affect the whole entire graph at once. And so I'm going to load a representation of the graph into memory using this this call, and then this is going to allow us to work on the whole graph at once in one command rather than individual hops at a time. So the thing to notice here, I'm calling create the graph, and I'm giving it a name. I'm going to call it MSA graph. I'm going to choose all the MSA nodes, and then here's where I would normally say what relationships I want to load into the graph. But remember, when we loaded our graph, all it has is nodes. There's no relationships at all so far. So I put an asterisk there, the star as a placeholder, to say, if you had any nodes, any relationships between the nodes, this is where you would go. But none are actually going to get loaded because there aren't any in our graph. And then finally, I'm going to tell it to load up the properties that were transformed with that log transformation. So this is going to move all of this from the graph on disk and read it into memory so that we're ready to work on the whole thing at once. So we'll click on that and run it. It takes just a second to read all of that into an in-memory version of the graph. And now we can call this scale properties function, and it says mutate. What that means is that it's going to modify that in-memory representation of the graph and add a new property. The new property that it's going to add is called scaled properties, and it's going to take a vector that has these 4 numbers in it, and it's going to apply the min-max scalar to each of the 4 numbers, and then it's going to return a new vector that it will call scaled properties. So we'll run this. It should be very quick. It was indeed very quick. All right. And finally, this new scaled properties vector is in the in-memory graph. What this is going to do is write out that calculation that we did back to the regular Neo4j graph that sits on disk. That way, if we turned off the database and came back later, that in-memory graph would disappear, but this now is written onto the disk where it will stay. Great. Now that we have those scaled properties, we're going to use them to create a new relationship in the graph. So up until now, we've had no relationships in the graph, but we're going to create them. And so we're going to match all of the MSAs and then collect that scaled properties as the weight. And then we call this similarity algorithm, and it's going to write, which means it's going to actually store the new relationships on the disk. We're going to pass in the data that we collected up above, and then top K says that for each node, I want to look for the 12 other nodes that are most similar, that are closest to it in this Euclidean space. And we're going to create a relationship for them that is called is_similar. And then I'm going to write out a property, which is that distance value. So this is going to be a float, a continuous valued property representing the output of that Euclidean distance formula. So we'll run this. Great, so it created 4,704 pairs. I can see over here now I have these is_similar relationships that are new relationship types in my graph. And the minimum distance between them was 0.0038. The maximum distance was 0.53. The average was 0.113, and the median was 0.09. So the minimum distance means that these two things are really close together. And what we're going to do is create another property on that relationship, which is called similarity, because with the distance property, the lower the value, the closer they are. And we're just going to flip that around and make a similarity property that says the higher the value, the closer these two nodes are to each other. So it's the same number, just a different way to think about it as a similarity measure instead of a distance measure. So these ones that have a distance of 0.003 are going to end up with a similarity that is very close to 1. And the ones that had a distance of 0.53 are going to have a similarity that is around 0.47. So we'll run that. So we set all those new properties. And now, the final thing that we're going to do to kind of prepare our graph is rank these relationships. So I'm going to find for each MSA all the is_similar relationships, and then I'm going to sort them in order of similarity from the most similar to the least similar. And then what I'm going to do is create a new property on that relationship called rank. And it's just going to be a number from 1 up to 12, representing kind of the ordering of the most similar to the least similar for that particular node. And again, we don't have to do some kind of alter table. I just am adding a new property onto this relationship as we're evolving the schema of the graph to match our project as we think about it. There we go. Okay, so the next step that we're going to do is take a look at our graph. We could look at it here in Neo4j browser if I wanted to write a cipher query and start to look at the results and see how these different cities are similar to each other. But we have a tool that makes this exploration much easier and more intuitive, and that is called Neo4j Bloom. So if I come back here to my sandbox tab and then say open with Bloom, I'm going to copy the password here so I can remember it, and then in just a second it's going to open Neo4j Bloom for me. I'm going to put in the username, Neo4j, and then the password, and connect. So when Bloom opens up, it's going to ask me about a perspective. And a perspective is just a way that we tell Bloom how we want to format the look of the graph that we're creating. So I'm going to tell it here to create a perspective. And then I'm going to ask it to just generate a perspective. In other words, I'm going to ask it to guess. Make its best guess about what it thinks the perspective should look like. And then I'm going to tell it to use this perspective. Okay. And before we go too far, I'm going to come over here on the right side to the relationships and add a rule to the styling of these relationships. So I click on this line next to is similar. And I'm going to create a rule-based styling. And I'm going to style these relationships based on the similarity. And I want to range on the size. So we saw that the least similar nodes were about 0.47 and the 0.47, and the most similar was almost 1. I'm going to make the least similar ones a very light line, and the most similar ones I'm going to make a very heavy line. And then I'm going to toggle this to apply the rule. So now I have a rule-based style in place that's going to affect the way that those is similar relationships look when I search for them in the graph. Now I'm going to come here and say search the graph, and I'm going to search for New York. New York, very good. And then Bloom is going to give me some options for different patterns that relate to that New York City node. So I want to see everything that is similar to New York. So I just bring up that pattern in the search box, and then I press enter. And there we go. So Bloom found for me New York City and then the 12 other cities that were most similar to New York. And I can tell that the relationship to Los Angeles is stronger than the relationship to Dallas because of the weight of these lines. This line is heavier compared to this one. So that's interesting already by itself to see the way that these cities are related to each other. I noticed that in some cases, there's an arrow that goes both directions between New York to Los Angeles and Los Angeles to New York. But in other cases, the arrow only goes in one direction. And that's because when we ran that similarity algorithm and we said the top k equals 12, the outbound links represent the 12 most similar cities to New York. But then the inbound links represent, like here, it represents the 12 most similar cities to Los Angeles. So if I made a list of the 12 most similar cities to New York, San Diego is on that list. But if I made a list of the 12 most similar cities to San Diego, New York is not on the list. That's because there are other smaller cities that are more similar to San Diego than New York is. And so the top 12 for San Diego is different. If I want to see the top 12 for San Diego, I can just click here and say expand is similar. Okay, and that gets, now I can tell which are the top 12 for San Diego, and there's a few other ones: Oxnard, California, Honolulu, Hawaii, Bridgeport, Connecticut. Those all made the list. So I'm going to clear the scene because that got a little bit more complicated with San Diego and bring up this New York thing again. Another way we can explore this data in Bloom is to come over here and click this Show Filters button. So if I come here and say add a filter, I want to add a filter on the is similar relationships, and I am going to filter by rank. And then I'm going to say that the rank has to be less than or equal to 5. So I'm going to see the top 5 most similar cities to New York. So when I click apply filter, the ones that had a rank of less than 5 get grayed out. And if I want to, I can even dismiss those ones that were grayed out, and I can see prominently the 5 most similar cities to New York. And then I can come here and change this to see which ones drop out. So number 5 was Chicago, and then that drops out. And the number 4 was Seattle. Number 3 was Washington, D.C. Number 2 was Boston, and number 1 is Los Angeles. So that's just another way that we can explore these similarity relationships with a filter like that. All right, so we could have fun exploring all the different cities in the United States. I live in Kansas City, Missouri, and so I could look up any metropolitan statistical area that you want to. But let's go back to Neo4j browser, and we will do a little more exploration here. Oh, wait, before we do that, let's do something even a little bit more wild. I'm going to clear the screen. Clear the scene, I mean. Let's just search for all the MSAs that we loaded. So this query says, just show me anything that's an MSA. There they all are. And then I'm going to do Command A and select them all. And then if I say expand here and expand all of the is-similar relationships, whoa, we get quite an interesting blob, I guess we could say. It looks like a blob to me. But one thing about it is that it's not just a total circle, that it's like there's certain areas where there's a lot of dense connections, and then there's some other areas around out here where the connections are not as heavy. They're not as many of them, and they're not quite so heavy. So it looks like there might be some, this kind of looks like maybe the start of a cluster here. And if I come back to the filter and turn on the filtering again, and I'm going to filter these is-similar relationships on no, I'm sorry, how about on the rank? And let's say less than or equal to, we'll say the top 5 again. I'll apply that filter, and now I'm going to dismiss the filtered elements. You see, I can come down here to the bottom and say dismiss the filtered elements, and it starts to redraw the graph. And now when I take away some of that density, I can definitely see some different spaces within the graph that look like they might be forming their own communities. Like, look at this down here. There's just this little area. I'm going to zoom in on that and see what's going on down here. Okay, Puerto Rico, Puerto Rico, Puerto Rico. So all of these groups in this little area are all part of metropolitan statistical areas in the United States territory of Puerto Rico. You can imagine that they have a lot in common with each other, more than they would perhaps in other areas, and looks like they're connected to San Juan, also in Puerto Rico. So this is giving me a hint that there are probably some communities within this graph that we could explore in greater detail by using a community detection algorithm that comes with Neo4j. This looks like it must be some kind of an interesting community up here in the corner as well. So I'm excited to go look and see what we can find when we explore this. So I'm just going to skip ahead a few slides. Now here, we're going to create another in-memory graph with the graph data science library. And so I'm going to call this GDS graph create again. And this is going to create a new graph. And it's going to bring in all the MSA nodes. And also it's going to bring in all the is-similar relationships. Remember, last time we created this in-memory graph, we didn't have any relationships. We just put a star there. But now we've created new relationships. So I'm going to tell it what kind of relationship to bring in. And then on those relationships, I want to bring in that similarity property as a numeric value. So I'll run this. There we go. So we created the in-memory graph. Now we're going to run a community detection algorithm called Louvain. And we're going to tell this that we want to write the communities that it detects back out to the graph on disk. So it's going to calculate them in memory, and then we want to store them so that we can look at them in Bloom. So it's going to write is the write mode, and then we're going to use the MSA similarity graph, and the relationship weight property to use for the calculation is that similarity value. And we're going to store a new property called community ID. And then just to make things a little bit easier for me to read, I decided to make the community IDs be consecutive numbers from 0 up to however far it goes. This isn't really necessary. Those ID numbers don't have any special meaning, and so they could be any number at all. But just to make it a little easier to read, I told it to make it consecutive IDs. So we'll run this. There we go. So it found 6 communities within the graph. And then this modularities is a statistic that tells us how much more we're seeing connections inside the communities than we would expect to see if those relationships were just distributed at random across the graph. And this algorithm is an iterative algorithm. And so every time it cycles through, we should see this modularity number getting higher. And so we can see that it went from 0.62 to 0.67. So that looks like a successful run. So now I'm going to run this query that's going to tell me some statistics about the clusters that were discovered. And it's going to tell me the number of items that were in there, the average population, average home price, average income, the average percentage of people with a bachelor's degree. And then it's going to give me 3 examples of cities that were found within that cluster or within that community. So we can come down here and take a look at this, and we can see that I sorted them by most population to least population. So community 1 has an average population of 2 million, which is much bigger than the others. Community 3 has an average population of 380,000. Community 5, 280,000. So a fairly significant step change there. Also, it looks like community 5 has quite a bit higher home prices relative to community 3. And then we come down, and community 4 has even higher income than community 5 did, and definitely higher home prices as well on average. Community 2 is quite a bit smaller. Oh, look at this over on community 4 as well. They've got a way higher percentage bachelor's degree than those other smaller cities. So that's definitely kind of makes them stand out to me. Community 2 and community 0 are both pretty small cities, but community 0 has definitely cheaper houses and lower income. So that's probably the difference between community 2 and community 0. So in this next command here, what I'm going to do is just give those communities some friendly names. And I made these names up myself just based on what I observed about the different statistics there. You could call them whatever makes sense to you, but I'm going to just put these labels on there to help me remember kind of the patterns that I observed about what made each community different from the others. So we will run that. And then I'm going to create an index on that new property that we added to the graph. And this is going to make it searchable within Bloom. So I can search for the nodes now based on the MSA name, and I can also search it based on the MSA community name. So now let's go back here to Neo4j Bloom, and I'm going to click over here on the perspective toggle here, and then there's this thing that looks like a database that says refresh perspective. And what that's going to do is bring in the new property, because when we created this perspective the first time, that community name didn't exist, and now Bloom is aware of it, that there's a new property in the graph that it can use. And then I'm going to come over here to the nodes, and I'm going to do some styling on the nodes to make them stand out a little bit. So I click on add rule-based styling, and then I click here for the community name, and then unique values, and I want to do colors based on those unique values. So if I click apply color, now each different community has a different color in the graph. So that just got a lot more colorful. And I'm going to add another rule here, which is going to be based on the population. And I'm going to do a range rule, just like we did for the weight of the relationships. We're going to add a range rule for the size of the nodes. And yeah, the minimum was about 50,000. The maximum was 19 million. That's good. I'm going to make the maximum ones extra big, and the minimum ones can just be size 1. And we'll apply this. There we go. So now I'm going to clear the scene. And let's focus just on the nodes that got identified as college towns. So if I search for college towns, there we go. And I'm just going to press enter to bring those up. And I'm going to zoom in here and start to look a little bit. And I can see, based on what I know about United States geography, that this makes some sense. Lincoln, Nebraska is where the University of Nebraska is located. Charlottesville, Virginia is where the University of Virginia is located. Ames, Iowa is the city where I was born, and that's where Iowa State University is located. My father was studying at Iowa State when I was born there. Morgantown, West Virginia is the University of West Virginia. So I see a lot of Columbia, Missouri. That's the nearby university here in Missouri. Tallahassee, Florida, Florida State University. So Boulder, Colorado, University of Colorado. So I see a lot of metropolitan statistical areas that are dominated by high education group and medium-sized population. So it seems like our clustering makes some sense. So now I'm going to select all of these and expand them to find the things that are similar. And as we would expect, there's a lot of relationships among the yellow college town communities, but then it looks like there's also some. These purple ones are large metros. So Portland, Oregon, I can zoom in and see which other purple metros, Sacramento, San Diego, here's Bridgeport, Connecticut. I also ended up, if I zoom around the graph a little bit, I ended up with some of these orange ones. The orange ones are medium metros. So West Lafayette, Indiana, I think that's where Purdue University is. So definitely can see some connections there. Savannah, Georgia. What are these teal colored ones? These are our small middle income cities. So there's a few small middle income like Staunton, Virginia, Coeur d'Alene, Idaho. So we can have fun with this, exploring all different connections within the graph, and we can see how the community detection algorithm found some interesting patterns, and we can expand upon those patterns and easily traverse the graph. And as I'm doing all this expanding and traversing, I'm not even having to write any cipher as I do it in Bloom. I can just easily use the tools to explore these connections. So that, I think, takes us to the end of our slide deck. But even just with the data set that we've played with today, there's a lot of interesting ways that you could expand this. You could run it for the micropolitan statistical areas, or include the metropolitan and micropolitan statistical areas together. You could use different community detection algorithms. Neo4j supports multiple other ones. So you might try this with the node propagation, or the label propagation algorithm, to see how the communities come out differently versus the Louvain algorithm that we ran. We chose to apply those scalars, but min-max is not the only scalar that you could use when you do scale properties. You could use an L1 or an L2 scalar and get a slightly different shape to the data before you run the similarity graph and see how that impacts things. So there's all kinds of ways that you can play with this, and of course you can try it with your own data anytime that you have just a list of items and they have 2 or 3 or 4 different properties related to them. You could apply this to understand that hidden structure that is there in your data and explore it in a way that I feel like is very intuitive for a business user. You don't have to be writing code to be able to explore this, and it can help get that intuitive understanding of the data that sometimes is missing. If we just throw up a cluster that we generated in Python, it's hard to interrogate that and see why did Westminster end up yellow instead of blue. Well, when I look at, Winchester, Virginia, when I look at the connections, it has more and thicker connections to the yellow nodes than it does to the blue nodes. So that's why it ended up yellow instead of this light blue color. So hopefully it helps to demystify what's happening with these data science algorithms and make it something that your business users can have confidence in and something that they can interrogate on their own. Oops.
Cool, super. Thank you very much, Nathan. That was cool insights, good overview. I think we can. We hope that that this was insightful for you as well, and I think everybody can try it out. The links are in the description, so I think that's a good place to start than any to give it a try. I think this was very clear, and at least for me, very clear. There were no immediate questions in chat. I only saw a few Euclidean fans at the beginning, so I guess that was good. um, but other than that, as I don't see any immediate question, I think that's what we have for today. The links are in description, so I think Um, thank you for showing us through this, Nathan, and thank you for taking the time. And we will be back with another Aura session on Monday, Michael and I. Yes, the session question now. The session is interesting, so people are interested in. Yes, it will be recorded, or it has been recorded, so it's gonna be on YouTube in a few minutes for everybody that's watching it on other platforms. So yeah, what I wanted to say is we will be live back on Monday, Michael and I, with another session on our Aura streams. But I think that's it for today and for this week, actually. So thank you very much, Nathan, and thank you very much, everybody, for taking part in this. Take care, everybody. Bye.